If you want to, you can just
switch off now and you can watch the recording afterwards. But if you need to leave, I'm not gonna hold you. Well, we'll slow down and we'll do something. We'll do the next stuff gently. Okay, so we kind of proved the product formula, except we need to prove that phi is multiplicative. Okay, so now we'll go for the Euler's theorem. Now I set this up, I explained this yesterday. So Euler's theorem, this is theorem 5.7. This is why we're interested in studying this function and being able to evaluate this phi function using the product formula. Is because remember I said it's a multiple of the cycle lengths that powers of any element goes through. Okay? So Euler's theorem says if the GCD of A and N is 1, i.e. what that means is A is an element of the multiplicative group. Congruence classes modulo N. Yeah. Zn, the multiplicative group, consists of all the congruence classes that are coprime to N. Euler's theorem says that if you take A, raise it to the power phi of N, what you get is congruent to 1 modulo. It's equal to 1, equal to the identity in the group. And so this is what allows you, like we did when we investigated, we were working with small numbers in the tutorials, so we could find out these cycle lengths just by inspection. The cycle lengths meaning that the cycle of different elements that the powers of A would go through. If you look at A to the 0, which is 1, A to the 1 is A squared, A cubed. You're moving around in this finite group, so eventually you have to repeat values, and you always repeat back at 1. Proved that yesterday. So we get this cycle of values. And if we know the length of that cycle, then we can break down any, even ginormous power of A, because you just divide it by the cycle length. And you'll quiz around the cycle some complete number of times, and then you'll take some small number of extra steps. Now, it's a difficult problem to work out in general, to just given any element of the multiplicative group to work out its cycle length exactly. But what Euler's theorem tells us is this magical number, phi of N, which is just the size of this thing, it's a multiple of the cycle length. So when you raise A to this power phi of N, you're going around that cycle some exact number of times and arriving back at the starting point, which is A to the 0, which is back at the congruence class of 1. But before we prove Euler's theorem in general, we'll prove the special case. And the special case goes by the name of Fermat's little theorem. Not Fermat's last theorem, Fermat's little theorem. Fermat's little theorem says if P does not divide A, i.e. the GCD of A and P is 1, then A to the P minus 1 is congruent to 1 mod N, mod P. So this is the special case. It's just Euler's theorem where N is P. P, in number theory, meaning a prime number. Now this we can prove directly. Now in the notes, I give a proof which appeals to group theory. That's a little bit unsatisfying because we're using machinery that we haven't proved in the course. So this is a direct argument that just uses concepts that we've already built up. Okay. So what are we going to do? Yeah, we're going to consider what we're going to do is we're going to multiply together all the elements from the group ZP. So the multiplicative group ZP consists of the elements 1, 2, 3, all the way up as far as P minus 1. Okay. And we're going to think about multiplying them all together. But we're going to think of that in two in a kind of a clever way. So we let A be one of these numbers. So A is some number between 1 and p minus 1. And we consider these numbers. A, 2 times A, 3 times A, all the way up as far as p minus 1 times A. So we multiply all of the elements by A. Now the claim is, if I is different to J, well, my claim is that none of these elements are congruent to one another. They're all represent different congruence classes. So I'm claiming if I is different from J, and they're both of them between 1 and p minus 1, my claim is that AI is not congruent to AJ mod p. So we need a little proof of that, and the proof of that is a little proof by contradiction. So suppose AI were congruent to AJ mod p. Well, the definition of modulus says that, of congruence says that P divides the difference, AI minus AJ. So in other words, P divides A into I minus J. Now, P divides a product of two numbers. P is a prime number. We proved our very important step that enabled us to prove the fundamental theorem of arithmetic. You can almost take it as an alternative definition of a prime number. If a prime number P divides a product, what can you immediately declare or deduce from that? It must divide at least one of the factors. Okay? You can't make P divide the product by having a little bit of P in here and the other bit of P in this factor, because it's a prime number. You can't tear it apart. It's stuck together as one thing. You can't tear it apart into factors, except 1 times itself. Okay? So the only way the P can divide this product is if P divides one of the numbers. Now we know P does not divide A, because A is coming from the multiplicative group. So this implies P divides A, or P divides I minus J. But P does not divide A, by assumption at the start. Okay, A is coming from the multiplicative group, it's co-prime to A. And P cannot divide I minus J, because I and J are two numbers between 1 and p minus 1. So the furthest they can get apart is distance p minus 1. If one of them is at the beginning, the other one's at the end. But even then, they're only a distance p minus 1 apart, or p minus 2. Yeah, difference between them. So you can't have P dividing that number. The only way you could have P dividing a difference like this is if the difference was 0.
What exactly did you say that you can't divide I minus J?
Yeah, can't divide. How big can I minus J be? See, I and J are trapped between 1 and p minus 1. So the furthest you can get them apart is if one is at the beginning and the other one's at the end. But then the difference between them will only be p minus 2. Yeah, they can't get far enough apart. Yeah.
They can't get far enough apart.
No, they can't, because they're trapped in an interval of length p minus 1. And to be divisible by p, you need to get at least the distance p apart. If you're different, if the I and J are different. So the only way to really reconcile this with what we know about the prime numbers is if I is equal to J. But if I is equal to J, then obviously AI is congruent to AJ, because it is AJ. So this little proof by contradiction so that means this list of multiples of A all different modulo p. But they're all of them in Z. They're all of them in the multiplicative group. Because A started in the multiplicative group, and the multiples 1, 2, 3 up as far as p minus 1, they're all the elements of the multiplicative group. So each of the products is in the multiplicative group. And how many of them? There's exactly p minus 1 elements. So this must be all of the elements from the group. Okay? So they're all different modulo p. So they are, in some other mixed up order, they are the p minus 1 congruence classes from ZP. So that means, therefore, when you multiply them all together, you are in effect congruent to multiplying together all of the elements from the group of the multiplicative group of congruence classes. Okay. So the original list of congruence classes in ZP, the multiplicative group, you think of 1, 2, 3 up as far as p minus 1. But if you instead multiply them all by A, what you do is you mix up the congruence classes in some way. But you've still got a complete set of representatives there, because we just proved that no two of these are congruent to each other. So they must all live in different congruence classes. So they must occupy all of the congruence classes from the multiplicative group. So when we multiply them all together, we know that we're congruent to just multiplying together all the original congruence classes. But you see, you've got a common factor A in each of these factors. So that A can come outside, and it comes outside as A to the power p minus 1. Yeah, so you're multiplying together all those factors. There's an A in each factor, so you've got A to the power p minus 1 inside this big long product. So you can just take that outside. And actually, i.e., you think about this a better way, that's actually p minus 1 factorial. Yeah? It's the product of everything between 1 and p minus 1. It's the definition of p minus 1 factorial. Now, what are you tempted to do in this? You've got A times something equals the same something. It's not equal, it's congruent to, but just as an algebraic relation or equation, it's A times an X equals X. What's your temptation to do? Divide through by X. Can you divide through by p minus 1 factorial?
Yes.
Well, remember, this isn't an equation of numbers. If it was an equation of numbers, you could divide through as long as you knew the number was non-zero. But it's a congruence of integers. Well, yeah, you can. But so what do we mean by dividing through a congruence? What we mean by dividing through a congruence is multiplying both sides by the multiplicative inverse of the number that you want to cancel. Yeah. So is there a multiplicative inverse modulo p for p minus 1 factorial? Well, the condition for having a multiplicative inverse modulo p is that you are co-prime to p. Yeah, we described that when we set up this group originally. Remember, we had to chuck out, when we were setting up Zn, the multiplicative group Zn, we had to get rid of everything that wasn't co-prime to n. So if you weren't co-prime to n, you didn't have a multiplicative inverse modulo n. So we can cancel p minus 1 factorial from both sides if the GCD of p minus 1 factorial and p is equal to 1. It's co-prime to 1. Because that's when things have multiplicative inverses. Is p minus 1 factorial co-prime to p? Yeah, why? Got you, yeah. P isn't any odd number, is it?
P is a prime number.
P is a prime number.
So none of the numbers lower than it divided into P.
Yeah.
So if you multiply all those.
And none of them are divisible by p.
Yeah.
So when you multiply them all together, there's still no p here. There's still no factor of p here. If there was, it must be that it was brought into being by multiplying two different things. But p is a prime number. It isn't the product of two different things. P minus 1 factorial is co-prime to p, since p is prime. Okay, p wasn't a prime number, then, n minus 1 factorial will most of the time not be co-prime to n. Because if n has loads of factors, then you'll be multiplying those factors when you look at the factorial. But p doesn't have any factors apart from itself and 1. So when you multiply all the numbers together between 1 and p minus 1, you're not multiplying. There's no p here. Okay. So we can cancel the p minus 1 factorial on both sides. So we get that a to the p minus 1 is congruent to 1 modulo p. So when we multiply both sides by the multiplicative inverse of p minus 1 factorial, we get a to the p minus 1 on the left, and we get the congruence class of 1 on the right. Okay, so a to the p minus 1 is congruent to 1 modulo p. So that's the proof of Fermat's little theorem. Now this exact same argument can be extended to Euler's theorem. It's really essentially the same argument. Generalize this argument to prove Euler's theorem. That GCD of a and n is 1, so if a is in the multiplicative group, then a to the power of phi of n is congruent to 1 modulo n. That says that phi of n must be some multiple of the true cycle length of a. Okay. When you raise a to that power, you're back at the starting point 1. So you may have gone around the true cycle a number of times, but you've done it exactly and arrived back at the starting point. And as we've described in the tutorial and yesterday, so knowing the value of phi of n allows us to simplify a to the power b modulo n, even when b is ginormous. Okay? So even when b is so big that no computer can compute directly a to that power, it doesn't have enough storage or time. But if you know the value of phi of n, then you can simplify the large exponent to something less than phi of n and quickly work out the congruence class of a to the power b modulo n. Okay, and this lies behind some of the cryptographic techniques that modern cryptography relies on. John will discuss this with you in detail when you come on to these things. But the basic idea is that has he discussed the basic idea of public key cryptography?
No.
With you? Yeah, so. Yeah, it's going to be next term, but the basic idea, like in 1 or 2 minutes, is that I can take two very large prime numbers. Okay, so we have databases of millions of prime numbers available. I can select two very large prime numbers from that list, and I can multiply them together and find out what n is. And then I can publish the value of n on my website. And anybody who wants to send me an encrypted message encodes their message and sends it to me as information modulo n. Or as information to do with, exponents of a modulo n. I'm not doing a very good job describing this. But the thing is, it's set up so that to decrypt the information, you need to know the value of phi of n. Now, I know the value of phi of n because I know that n is the product of two primes that I've chosen in private myself. I didn't disclose it to anybody. Not even my wife. It's completely secret. It's just stored in my head. But even though I published n, because factoring is hard, you, the public, can't work out what those prime factors are in a reasonable amount of time. You don't have time, you don't have the computing power. And so you can't get at the value of phi of n in a reasonable time. So the value of phi of n is secure because only I know it, because only I know the prime factors that I use to form the number n. But anybody can send me encrypted messages because encrypting the message, you just need to work modulo n, but you set it up so that to decrypt it, you need to know this special value, which allows you to simplify large powers, modulo n. But that's just the rough feeling of the idea behind it. You will investigate all the details very carefully with John in due course. Okay. But you should take that as an extra exercise to be working on at the moment, is to construct the general proof for Euler's theorem for this. Okay, you can use it using the same idea that we just used for Fermat's little theorem, just extend and generalize the ideas. Okay, okay, we'll finish there.